Okay, so imagine you've got this really complex workshop, right? Raw stuff comes in one end,
Yeah.
and it goes through all these different stations getting worked on until, boom, a finished product comes out the other side. Our brains, they kind of work like that too, processing information in stages.
That's a great analogy. And today we're diving into the digital version of that workshop, multi-layered neural networks.
Exactly. So what is a neural network, fundamentally?
Well, think of it like a computer system that's inspired by how the brain is wired. It uses lots of these simple little units, we call them artificial neurons, all connected up.
Connected, okay.
And the cool part is they learn patterns from data all by themselves. You don't have to write explicit code for every single possibility, like figuring out if a photo has a cat in it just by looking at tons of cat pictures. It sort of teaches itself the rules.
It figures out catness on its own. That's
Yeah.
wow. Okay, so for this deep dive, let's map out the journey the data takes. There's an entry point,
Input layer, yeah.
the middle bits,
Yeah.
the hidden layers. That sounds intriguing. That's where a lot of the magic happens, you could say.
And finally, the result pops out at the...
The output layer.
Yeah.
That gives you the final answer.
Got it. Input, hidden, output. Our plan today is to unpack all of this, make it clear, maybe even illuminating. So let's start at the beginning. The anatomy. What's this input layer all about?
Right, the input layer. It's simply the front door for your data. If you're feeding it an image, for instance, each pixel's value, its color, basically might be one input.
Okay, so one input per pixel.
Could be. Or if you have, say, spreadsheet data, each number in a row could be an input. It's just the raw information the network starts with. Nothing processed yet.
Just the raw materials arriving at the factory door. And then they head inside to the hidden layers. The sources called these the factory's inner stations. What actually goes on there?
This is where it gets really interesting. These hidden layers start to, well, make sense of the raw input. The first hidden layer might just pick out very basic feature.
Basic.
Like in an image, maybe it learns to spot simple edges or lines or maybe basic shapes. Really fundamental stuff.
Okay, edges and lines. Then what?
Then the data moves to the next hidden layer. And that layer takes those simple edges and lines and starts combining them. Maybe it learns to recognize corners or curves or textures.
Ah, I see. So it's building complexity.
Exactly. And if you have more hidden layers, they keep building. A later layer might combine curves and corners to recognize, say, an eye or an ear or the shape of a nose.
So layer by layer, it's assembling a more complete picture. From lines to shapes to parts of a face, potentially.
Precisely. Each layer learns progressively more abstract features based on what the previous layer found. You can picture the flow. Raw data hits the input layer. Then it goes through hidden 1 for basic features. Then hidden 2 combines those, maybe more hidden layers,
Yeah.
until it reaches the end.
Which is the output layer. Okay, so after all that processing in the hidden layers, what does the output layer actually do?
It's the final step. It takes the highly processed information from the last hidden layer and gives you the network's conclusion.
The answer, basically.
Right. So in our cat photo example, the output might be a simple label, cat or not cat. Or, more often, it'll give you probabilities.
Probabilities, like how sure it is.
Exactly. It might say, okay, based on everything I've seen, there's an 88% chance this is a cat. It gives you a confidence level. That's the final result of the whole journey.
Okay, structure makes sense. Input, hidden layers, doing the heavy lifting step by step. Output gives the answer. But how does it learn to get the right answer? How does it figure out cats from dogs?
Let's dig into the learning mechanics.
Okay, so the first part is called the feed-forward pass. Think of your input data starting its journey down that assembly line we talked about.
Okay, data's moving forward.
Right. And at each connection point between neurons, something happens. Each neuron takes the signals coming in, multiplies each one by a weight. You can think of the weight as how important that specific input connection is.
Importance, okay, like a measure of influence. Then it adds something called a bias. So it's kind of like a little nudge, letting the neuron activate more
A
easily.
nudge, right.
And finally, there's an activation rule or function. It looks at the combined weighted inputs plus the bias and decides, does this neuron fire? Does it pass a signal on to the next layer, or does it stay quiet?
So inputs get weighted, nudged by a bias, and then there's a decision, pass or block. And this happens at every single neuron as the data flows through.
Pretty much, yeah. The signal propagates forward, layer by layer, getting transformed at each step until it reaches the output.
Okay, but how does it know if the final output is any good? If it's right or wrong?
That's the next crucial step, measuring the error. Once the network makes its prediction, let's say it predicts dog, but the picture was actually a cat.
Oops.
Exactly. We compare the network's prediction, dog, to the correct answer, the ground truth, cat. The difference between them, that's the error. It's a measure of how far off the network was.
And it doesn't just note the error, it uses it, right? This is where backpropagation comes in. Sounds complicated.
The name sounds a bit technical, but the idea is actually pretty intuitive. You take that error value you just calculated,
The oops signal.
kinda, yeah, and you send it backward through the network, from the output layer, back through the hidden layers, all the way towards the input.
Sending the error back up the chain.
Exactly. And as that error signal travels back, each neuron looks at the contribution it made to the final error and adjusts its weights and biases just a tiny bit,
Adjust them how?
in a way that's calculated to reduce that specific error next time it sees a similar input. It's trying to correct its mistake for the future.
So it's like feedback. It gets told you were wrong by this much, and everyone involved adjusts slightly so they're less wrong next time.
That's a great way to put it. It's learning from its mistakes. Our source mentioned learning to ride a bike, didn't it?
It did. You wobble, you almost fall, you make tiny adjustments to your balance. Try again.
And eventually, through lots of little corrections based on those errors, the wobbles, you learn to stay upright. Neural networks learn in a very similar way. Feed forward, check the error, backpropagate the error to make adjustments, repeat thousands, maybe millions of times with different data.
Trial, error, and gradual correction. Got it. Now, we keep saying multi-layered. Why is that so important? What's wrong with just like one hidden layer, a shallow network?
That's a key point. A shallow network, one with only a single hidden layer, is fundamentally limited in the kind of patterns it can learn. It can maybe learn simple, direct relationships.
Like the source said, if it's red, then it's an apple.
Exactly. Very straightforward rules.
Yeah.
But the real world is usually way more complex than that, isn't it?
Definitely. An apple isn't just red.
Right. And that's where deep networks, ones with multiple hidden layers, really shine. Because each layer builds on the previous one, they can learn these hierarchical features.
Hierarchical, meaning
Meaning they learn simple things first, then combine them into slightly more complex things, then combine those into even more complex things. So it doesn't just learn red. It can learn red and round and has a little stem thingy. It learns the combination of features across layers.
okay. So more layers equals the ability to grasp more complicated, nuanced patterns, like having more specialized tools or stations in our factory.
Precisely. The depth allows for a richer, more layered understanding of the data. It can capture relationships that a shallow network would completely miss.
Okay, let's make this concrete. A really common example is recognizing handwritten digits, right? Like for mail sorting or unlocking phones. How would a multi-layered network tackle that?
Right, good example. So the input would typically be an image of the digit, maybe like a 28 by 28 grid of pixels. That's what, 784 input values?
Lots of inputs. Okay, then the hidden layers get to work.
Yep. And think about what they might learn. The first hidden layer, seeing those pixels, might just learn to detect tiny line segments, horizontal ones, vertical ones, maybe diagonal ones, very basic stuff.
Just little lines. Okay.
Then the next layer might take those lines as input and learn to combine them. It might learn to spot curves or corners where lines meet, or maybe complete loops.
So combining lines into curves and loops, I can see where this is going.
Exactly. And then maybe a deeper layer learns to recognize combinations of those curves and loops as characteristic parts of digits, like the closed loop at the bottom of a 6, or the 2 loops in an 8, or the straight vertical line of a 1.
It's like it's learning the essential building blocks of each digit.
That's a perfect way to describe it. It decomposes the digit visually and then learns to recognize it based on these learned components.
And the output layer, how does that work for digits?
For digit recognition, you typically have 10 output neurons, one for each digit, 0 through 9.
Okay, 1 neuron per digit.
And the output of each neuron is basically a probability score. The neuron for 7 fin might output, say, 0.92, while the others output very low values.
So the highest score wins. That's the network's guess.
Exactly. The network says, I'm 92% confident this image is the digit 7. And the amazing thing is, after training on thousands, maybe millions, of labeled examples of handwritten digits.
Labeled meaning someone already said this picture is a 7, this one is a 2.
Correct. After seeing all those examples and going through that whole feed-forward backpropagation loop countless times, it gets really, really good at classifying digits it's never seen before.
That's pretty incredible. And this layered approach isn't just for digits, is it? You hear about these networks everywhere.
Oh, absolutely. The applications are vast and growing all the time. We've talked about image recognition that's behind things like Face Unlock on your phone,
Huh.
but also analyzing medical scans like X-rays or MRIs, helping doctors spot things. And self-driving cars use it constantly to see pedestrians, other cars, traffic lights.
Right, vision systems. What about hearing?
Speech recognition. When you talk to Siri or Alexa or Google Assistant, those are powered by deep neural networks that turn your spoken words into commands the machine can understand.
Makes sense. And translation.
Yep, language translation too. Translating text from, say, English to French online often involves sophisticated, multi-layered networks.
And those uncanny recommendations we get, like, you watch this movie, you might like these.
Recommendation engines, exactly. Analyzing your past behavior, what you've watched, bought, listened to, and predicting what else you might like. Neural networks are very good at finding those subtle patterns in user preferences.
It really is everywhere. Okay, before we wrap up, you mentioned some key terms. Maybe we could do a quick glossary rundown. People hear these words thrown around.
Good idea. Let's hit the main ones quickly. Epoch, that's just one full pass of the entire training data set through the network. You usually train for many epochs.
Okay, one full run-through is an epoch. What about batch?
Instead of processing the entire data set at once, which can be huge, you often process it in smaller chunks. A batch is one of those chunks. The network updates its weights after each batch.
Got it. Smaller chunks. Then there's overfitting. That sounds bad.
It can be. Overfitting is when the network learns the training data too well. Like, it memorizes the specific examples, including noise and quirks, but then it fails to generalize to new, unseen data. It's like acing the practice test, but flunking the real exam.
Ah, okay. Memorizing instead of understanding. And regularization.
Regularization covers techniques used to prevent overfitting. Things like adding penalties for weights getting too large, basically trying to keep the model simpler and more general.
Okay, ways to stop it memorizing. Last one, learning rate.
Crucial one. The learning rate controls how big the adjustments to the weights and biases are during backpropagation. Too big, and the learning can be unstable. Too small, and it can take forever to learn. Finding a good learning rate is key.
Okay, epoch, batch, overfitting, regularization, learning rate. Helpful definitions. So let's try and summarize the big picture from today's deep dive.
Sounds good.
Multi-layered neural networks are these computing systems fundamentally inspired by our own brains.
Right, using layers of these simple processing units, the neurons.
And they learn complex patterns directly from data. They don't need every rule spelled out. They figure it out through essentially trial and error on a massive scale.
Exactly. That feed-forward pass, measuring the error, and then backpropagation to make those tiny adjustments. Repeat, repeat, repeat.
And the multi-layered part is key because having multiple hidden layers allows them to build up understanding step by step from simple features to really complex concepts.
Which is what lets them do these amazing things like recognizing images, understanding speech, translating languages, making recommendations, all that stuff we talked about.
Absolutely. Now, if you listening want to explore this more, what are some next steps?
Well, one really fun thing is to find an online demo. There are websites where you can just upload a photo, and a pre-trained network will tell you what it thinks is in it. It makes it very tangible.
Yeah, seeing it actually work is pretty cool.
Another thing, maybe slightly more advanced but really insightful, is to look for visualizations of what the hidden layers are actually detecting those activations. You can sometimes see how it starts with edges and builds up to more complex shapes. It helps demystify the black box a bit.
Seeing inside the factory stations. I like that.
Mm-hmm.
So perhaps the final thought to leave you with is this. While these networks power incredibly complex applications and can seem almost magical,
Yeah, they can definitely feel that way sometimes.
remember what's at the heart of it. It's fundamentally a series of many, many simple calculations repeated over and over. It's not really magic. It's more like organized curiosity scaled up massively. Something to think about next time your phone recognizes your face. Thanks for joining us for this deep dive.